Okay, let's talk our notes for the day. So up till now, we've more or less talked about solutions and numerical concentration. We've tried to assign a number to things, either in moles per liter, weight over volume, or parts per million. We've been trying to numerically quantify solutions. But there's actually another way that we can quantify solutions. It's the pH scale. You guys have heard of this before, right? pH scale. Most people have seen a picture like this before. It's extended there. Anyways, most people have seen a picture like this before where they give you a pH range where it usually goes from 0 to 14. The number in the middle is 7, and if you guys don't know, 7 is usually considered to be neutral. Where are the acids? Which side? To the left. Yeah. So these guys here are the acids, and these guys here are the bases. Which is kind of confusing at first because you're like, hang on, shouldn't a higher number be like more acidic? But I have an explanation for that. I'll talk to you about that in a second as to why that works. Okay, but this is a second way that we can try to rank pretty much all solutions. Now, not everything is either going to be an acid or a base. Some things are neutral. And when we do our lab on Thursday, you're going to discover that many things should have a pH of basically 7. But if it's acidic or if it's basic, then we should be able to assign either a lower or higher number. Very good. So this is a general list that you might have even seen in grade 10, some basic properties of acids and bases. I mean, I don't have a ton to add other than you can read some of these ones. So acids, they're corrosive, they're soluble, they conduct. Do you guys know this one here? Acids turn litmus red. We're going to do this in our lab on Thursday, so long as I get litmus paper in time. If it's an acid, it'll turn litmus red, whereas a base turns litmus blue. Have you guys heard that before? The way I was taught to learn it, bases, B, blue. They both start with B. So bases are blue, acids are red. Okay, I want to talk about some theory here. Scientists have known about acids and bases for years. Okay, I want to use two words here. I don't actually have them on my slides, but let me write them down here for you. The word is empirical, and then the other word is theoretical. Before I talk about Arrhenius, I want to do a little bit of background information. There's empirical and there's theoretical explanations for things. Okay. Empirical evidence would be like lab evidence, where scientists were able to combine acids together because all acids are corrosive. They all react with zinc to produce bubbles. They all turn litmus red. And so if you had a way of testing a chemical in a lab, you can prove it's an acid by doing tests on it. Does that make sense? That's empirical evidence. And so it's actually very easy to test whether something's an acid or a base. All you need is litmus paper. Does that make sense? That would be an example of an empirical test. However, good science would require that you should be able to figure it out in theory as well. And you should be able to make a prediction before you use the litmus paper. You know what I'm saying here? Because what happens if I don't have litmus paper nearby? What happens if I have a substance and I say this is sodium hydroxide? Is sodium hydroxide an acid or a base? Well, you guys know it's a base, but why do you know it's a base? You didn't just grab a beaker of sodium hydroxide and put litmus in it. You knew it was a base because it ends in hydroxide. That's a theoretical explanation for things. See the difference between the two? One of them is based purely on tests, lab work. The other one, though, is we should be able to come up with a theory that describes things in general. And so now that I've given you that background information, I want to talk about Sponte Arrhenius. Okay. Prior to Arrhenius, they knew all about acids because they could do tests on them. And they recognized that this was an acid, and this was an acid, and this was an acid, because they all reacted the same way. And this is a base, and this is a base, because they all react the same way. And this one's neutral because it doesn't do that. But how do we put it on paper? And so Arrhenius has an idea. He thinks that it has to do with dissociation and ionization. Some words here. And this is why we're doing this after we've learned these words. Okay. Arrhenius had an idea. He figured that when dissociation occurs, we can then use that to figure out whether something is an acid or a base. And you guys already know this one, I think. Here's Arrhenius' suggestion. He figured that if sodium hydroxide could be shown on paper to break up into Na and OH, then this OH right here would mean that something is a base. If we can dissociate it on paper and ended in OH, that's a base. Now, this was actually good because let me give you a counter example. What if I gave you CH3OH? People look at this and they say, hey, it ends in OH. But just because it ends in OH, doesn't that mean that it's actually a base? And according to Arrhenius, he said, no. It's all about the dissociation. Do you guys see how these two things, they literally dissociated into pieces? Can CH3OH dissociate? No. Why? Yeah, they're all nonmetals. Right? In order to dissociate, what do you need to have? Ionic compounds. What do ionic compounds need to have? Metals and nonmetals, positives and negatives. CH3OH looks like NaOH, right? If I were to give this to my 5-year-old, she's smart enough to recognize letter combinations. She would say, look, they both end in OH, Daddy, therefore they must both be bases, right? And up until that point, no one had put this together that, what we really need to do is we need to dissociate them. Since this one here can be dissociated, I can prove it's a base. This one right here cannot dissociate, so that's why it's not a base. This would be a theoretical explanation that Arrhenius came up with for how to figure out whether something's an acid or base. Well, if bases have to dissociate, then acids need to ionize. And so we basically said, well, okay, same thing needs to occur then. If I have an acid, it needs to ionize and produce an H+. And if that's the case, then we consider it's an acid. But I have to be able to show on paper that it ionizes. So, on Thursday in our lab, what we're going to do is I'm going to give you guys a whole bunch of chemicals. And I'm going to tell you what they are. And so I'm going to say this one is NaOH. And I'm going to expect that you guys should be able to theoretically know what it is because you'll say NaOH, ends in OH, ionic. Ah, this is a base. But then I'm also going to give you lab tools, and I'm going to have you test to see whether it is a base. And hopefully we'll discover that the theoretical matches the empirical. Does that make sense? Now, when Arrhenius did this, he was focusing on the hydrogen ions, and really his tests were all about litmus. He was able to use litmus and figure out whether it turned paper red. Right? If blue turns red, it makes it an acid. But there were some problems here. Here's a good example of an acid that was a little bit trickier to work with. CH3COOH. Again, if I were to give this to Kinsey, she knows her letters. She would look at the end of it and say, hey, look, Daddy, it ends in OH. Things that end in OH are bases. But hang on a sec. What are the rest of these compounds? They're all nonmetals, right? So Arrhenius was finally able to explain that it doesn't have to start with the letter H. Most things start with H, but it doesn't have to. I can prove that CH3COOH can ionize into H+ and CH3COO-. So long as this thing right here is actually like a valid item. Is CH3COO- actually a polyatomic? What do we call it? Yeah, it's acetate. Right? And so now Arrhenius was able to explain, well, this is why acetic acid, vinegar, is an acid. Even though we write it ending in OH, it actually still can be proved to ionize. Here's another counterexample. This one right here, C6H12O6, you guys will recognize that as sugar. It has hydrogens in its formula. But does that mean it's an acid or a base? Well, no. We can't just say, hey, look, there's an H or an OH. We have to be a little more discerning here. So, here's a slide I have just talking about bases in general here. Bases, then, the key is that we want to have the hydroxide ion. I think I threw this slide on here just to make sure it's clear. You guys have heard that bases neutralize acids? Cool, I'm going to stop there. I just need you to have heard that before. Bases neutralize acids. Because I want to focus more on that concept in a second here. Water is actually an acid and a base. It's actually a really, really confusing concept here. Water actually has the ability to literally break apart. You know how water is H2O, which is HOH? Water actually has the ability to ionize and break off into an H+ and an OH-. Water is actually an acid and a base. And I believe I've shown you this before. You guys know that table in your book that has a list of all of the acids from strongest to weakest? Water is actually the weakest of all of the acids, but it is actually acidic. It's also equally as basic, right? Because really, since water can produce an acid and it can produce a base, what do acids and bases do to each other? They neutralize each other. And therefore, I can actually start to give you more of a theoretical explanation of why water has a pH of 7. We're going to do this tomorrow. I'm going to actually prove to you why water has a pH of 7. Here's what you need to know. Out of about 2 out of every billion water molecules actually break apart into pieces. So if you were to look at pure water, it's actually not pure water. If you had 2 billion, or if you had 1 billion water molecules, almost all of them would be water. But you would find 2 of them where they actually had broken apart. But here's the cool thing. Eventually, they're going to come back together. And another one's going to break apart. And then they're going to come back together and another one's going to break apart. Do you guys recall me talking about dynamic equilibrium in the previous section? That's actually going to occur here. So I'm going to come back to that concept more later, though. But I just wanted to point out that water is actually an acid and a base on paper. Okay, now Arrhenius has this great idea, and it works for the most part, but there was a problem. And up until the 1900s, where some really important experiments happened around the turn of the century here. Specifically, I'm talking about Rutherford's gold foil experiment. Do you guys remember Rutherford's gold foil? He discovered the nucleus. I mean, scientists, they didn't fully understand the total internal structure of matter yet, but as they started to realize more about electrons, protons, and eventually when James Chadwick found the neutron, they finally actually knew about all these different parts there. But I guess what I'm getting at is at the time, they didn't realize that hydrogen, H+, was literally a proton. Right? Hydrogen plus, H+, is literally a proton. And I've mentioned this before. A proton by itself is a subatomic particle, not very stable. Because really, where are protons supposed to be found? In the nucleus. Do nucleuses usually want to react? No, unless they're nuclear reactions, but we're not talking fission and fusion here, right? So scientists finally started realizing that it actually makes more sense to describe the hydrogen ion as bonding with water to make hydronium. And we talked about this before, I believe, right? The idea that a single hydrogen proton, very unstable. Literally, this is a nucleus, all by itself. It's been stripped away of its only electron. So what we like to do instead is rather than write H+, we write the hydronium instead. It's a better representation. 1 water takes 1 proton, and it becomes this guy instead. And so most of the reactions we write are going to be written with H3O+. But really, it wasn't until about 1900 that we actually figured this stuff out, because before that, they didn't even know about nucleuses yet, right? It wasn't until, what, 1907 that Rutherford found the nucleus? Okay, so here's my point then. The Arrhenius model then is now modified a little bit. For the most part, it was all about producing H+ or OH-. If you can show me that, it's acid or base. But now what we're going to do is we're going to try to figure out hydronium instead. So rather than trying to prove that there's an H+ in something, let's try to prove that we can do a hydronium. It's not really that much difficult. So let me do an example here. According to this modified Arrhenius theory then, here's the definitions. If you can take a substance and react it with water, and it produces hydronium, H3O+, we can call it an acid. But we have to react it with water. And bases are things that produce hydroxide. If you can produce one of these two things here, then that'll help prove whether it's an acid or a base. Oh, I got 10 minutes here. I'm going to skip to my last slide. I'm going to reverse engineer this thing. Can you guys find this slide here? This is what we're going to work on. Empirically, it's very easy to tell whether something's an acid or a base if you have lab equipment. Grab litmus paper. If it turns blue, it's a base. If it turns red, it's an acid. But on paper, can you make a prediction about whether it's an acid or a base? So I want to try a couple of examples with you guys here. I'll try to show you how this might look. So I'm actually going to skip and do them out of order, though, because I've skipped my slides a little bit here. Can I do the second one first? Because that one's easy. Lithium hydroxide. So you already recognize it's a base, but let's prove why it's a base. What kind of compound is lithium hydroxide? Ionic or covalent? So you have a metal and a non-metal. What do ionic compounds do? Do they ionize or dissociate? Okay, so let's dissociate it. There, it'll turn into Li+, and it'll turn into OH negative. Hey, look, OH negative. According to Arrhenius, I can now predict this will be a base, which you guys probably didn't need before. But does that subtle little tweak make sense, though? Is that it has to be able to dissociate into a base. It doesn't just have to end in OH, it has to dissociate into an OH. So this one's a base. Does that make sense? Okay, let me try another one here. I'm going to skip out of order. Let's do number 5 now. H2CO3. Because of the fact that you guys have some knowledge on this, you're probably looking at it going, it's an acid. Why would you think it's an acid based on previously learned stuff? Because it starts with hydrogen. But we need a better rule than just starts with hydrogen. It needs to be able to produce hydronium. So, first question, is this an ionic or molecular compound? Metals or non-metals? Actually, these are all non-metals, aren't they? So, can I dissociate this? No. See how this one's a metal and a non-metal? Hydrogen, carbon, and oxygen are all non-metals. So I have to ionize it. When I ionize it, I'm going to react it with water. Now, when I react it with water, I'm going to try to produce hydronium. Now, okay, say that I took the hydrogen off of this guy, and I put it onto this water right here. What would be left if I pulled one hydrogen off of this? I believe you'd have one hydrogen and the CO3, and it would have to be a negative sign. Here's the key question then. Is HCO3 minus, is that a valid polyatomic? So what you have to do is you have to grab your periodic table, look in the top section and find, is HCO3 actually like a thing? Like, does it actually exist? Can you find it up there? HCO3 minus?
Yep.
What's it called?
Hydrogen carbonate.
Okay. Or does it also say bicarbonate underneath it? No, okay. All right. Anyways, HCO3. You guys know what I'm talking about here? Let me steal a periodic table. Up here in the top section here, if you can find it, HCO3 is right there. It's called a hydrogen carbonate. So I've now been able to write a valid equation, and in doing so, see how I've made H3O plus right here? Well, now I've proven that I can ionize this, so this is an acid. Let me try a more challenging one. Let's try the first one now. So this one right here, most of you would have known this one was a base without me even telling you. I bet you most of you would have known that this one was an acid. Again, without me telling you. But what about the remaining three? Because this one here, and this one here, I'll spoil it here. One of them is neutral, but the other two are either an acid or a base. Based on what you've learned so far, I don't think you'd know, right? So let me show you how using Arrhenius' rules we can actually make a prediction. Let's use Ca2SO4. First of all, it shouldn't be Ca2SO4, it should just be CaSO4. CaSO4. All right, first question, CaSO4. Ionic or covalent? Yeah, right? Calcium's a metal. SO4 as a polyatomic ion is a non-metal. So the first thing I could do is I could dissociate it into Ca2 plus and SO4 2 negative. At this point here, have I either produced hydronium or hydroxide? Doesn't mean it's neutral though. This stuff's actually a base. Which then you give me a funny look and you're like, hang on, this is a base? What do bases need? Well, bases need hydroxides. There's clearly not a hydroxide anywhere near here. Watch this. I'm then going to take the SO4 that's now been dissociated. I'm going to write a second equation. I'm going to take SO4, and I'm going to look at this guy. It is covalently bonded, right? It's all nonmetals here. I'm going to react it with water. In the process of reacting it with water, I'm going to make an OH minus. Now, the OH minus is going to mean that this water right here is going to lose one of its hydrogens. And the hydrogen is going to leave water and go attach itself and make it HSO4 minus. And if you look on your data table, HSO4 minus is actually a valid polyatomic. It's called a hydrogen sulfate, I believe. Well, now look, I've managed to show you how I can get a base out of this. this guy right here was actually basic. But it was only basic once the SO4 reacted with water, took a hydrogen off water to make water into a base. I think this is one of the reasons why I wanted to point on this slide. Water is really H and OH. You can actually make water be the thing that turns into the base by ripping the hydrogen off of water and making the water into a base. So, although this thing right here, maybe you might argue that it's not basic, when you dissolve it in water, it is a base, because it breaks up into two ionic pieces. This piece right here steals a hydrogen proton away from water. The water becomes OH minus, and HSO4 is a valid polyatomic. That makes sense. Let me do one more here, then I'm going to go back to my notes that I skipped here. Let's do CH4. You guys know what CH4 is? I mean, in terms of what we call it? That's methane. Methane's actually neutral. If we were to try to test the pH of methane, it'll be neutral. And now I'm going to prove to you why we know it's neutral. Okay. If it's going to be an acid, I have to make it equal an H3O+. If it's a base, I need to somehow make an OH-. If I can't get either of those, it must be neutral. Okay. And I'm going to show you why neither is possible. First question here, is this ionic or covalent? So I can't ionize it and break it up into pieces. The only thing I can do left is add it to water. Now I'm going to try my best and make it an acid. So let's say I wrote H3O+. I'm going to try to make it an acid. What would the other byproduct have to be if H3O became H3O+ and added an extra proton? Okay, well, if this guy gets an extra hydrogen, who did it come from? This guy right here, right? So now there's one less hydrogen on this guy, so now he'd be CH3 negative. Is CH3 negative a valid polyatomic on your list of polyatomics? No, it's not. Okay, which means that's not going to happen. Okay, so it's not an acid. What if it's a base? Let's try the exact same thing. Let's take CH4. Let's add it to water.
Can you please call 3500? Marty Duncan, please
Well,
call 3500.
what if we tried to pretend that it's a base and turn it into OH-? This would require the hydrogen going from the water over to this guy here, meaning that the HOH just becomes the OH and the hydrogen leaves. Well, then the other logical byproduct would have to be CH5 positive. Is CH5 positive a thing? Really, the key to this is that you have to look at the other byproducts and say, are these valid? And since CH5 is not a thing, really, I can't make this react with water and produce something that's considered stable, so therefore it's neutral. Okay. I'm running out of time here. I need to give myself 5 more minutes. Let me go back to a couple slides I skipped, and then we'll call it a day here. Let's go to this one here. Give me 2 minutes, and then I'll stop. This basically is going to show you the process that we just went through here. Let me give you this compound right here, NaHSO4. Previously, you would have been taught to look for starting with hydrogen as an acid or ending with OH as a base. But according to modified Arrhenius theories, we're looking for something a little bit different. The first thing you'd do is you'd say, well, is this ionic or covalent? It's ionic. Does that make sense? Because it's ionic, right here, I'm going to dissociate. In the process of dissociating it, did I produce hydronium or hydroxide? No. Doesn't mean I'm done. I mean, if I make one of those two right off the bat, that's awesome. But since I didn't, I'm not done. Here's what I did. I took this guy right here, and I tried reacting this guy with water. Check this out. If I take the HSO4 minus and react it with water, the hydrogen off of the SO4, I brought it over here and attached it to water to make hydrogen. Key question though, what happens when you rip the hydrogen off of this guy right here? Well, it gives you SO4 2 minus. Is this a valid thing? Is SO4 an actual thing? Yeah. Okay. Is CH5 plus a valid thing though? So since this one right here is valid, then, hey look, I was able to prove that this thing is acidic. I'm going to leave that there for right now. We'll pick this concept up tomorrow. This is what our lab is going to be on Thursday. Okay? What I'm going to do is I'm going to give you 10 compounds. I'm going to tell you what they are. I would like for you to, on paper, make a prediction as to whether it's an acid, base, or neutral. Then I'm going to give you testing supplies, and you're going to confirm. On paper, it's theoretical. In a lab, you've now done empirical tests. Ideally, this is the last thing I'm going to finish with here. I pulled a quote out of your book here. Scientists regard a theory as acceptable only if it can predict results. And that's really what I want to be able to do now, is use Arrhenius' theory and say, I'm going to, on paper, try to make a prediction. Hopefully we're actually correct about it. That's what good science would be. Okay, any questions before we take off here? Okay, sounds good. Tomorrow we'll pick this up. Wednesday's a work day, and then Thursday we'll try another lab. So, we'll talk to you guys later.